All right, let's continue our discussion here with sections 21.4, 21.5, and 21.6. In 21.4, we're going to discuss Lenz's law. Now, just as we did with Faraday's law, it said that the magnitude of the changing magnetic flux with respect to time is going to be the same as the EMF. This adds a directional component to that. So just as with all vectors that are have both magnitude and direction, we've discussed the magnitude of the EMF up to this point due to the changing magnetic field, but or due to the changing magnetic flux, I should say. But we haven't discussed the direction. Well, that's where Lenz's law comes in. So Lenz's law states that an induced current, or EMF, always acts to oppose the change that caused it. So let's read that again. It states that an induced current, or EMF, always acts to oppose the change that caused it. Lenz's law can be derived from Faraday's law and is a convenient way to determine the correct sign for any induced effect. So you've got a magnet here that is approaching this piece of wire. And what you are going to see is that the magnetic field is increasing. At time 1, the flux was this, but at time 2, it's going to be this. The amount of change in between time 1 and time 2 is this. Nature doesn't like it when you start changing things when it comes to electric currents or magnetic fields or things of that sort. So when you go through and in this particular case, when you have a changing magnetic flux, nature wants to keep the flux to be the same as it was. It's trying to resist the change. So because of that, there's going to be a current that's going to be induced in this particular ring. And that current that is induced is going to basically resist or push back against the current or the changing flux that we saw this way. That magnetic field that is produced from this current is going to resist that change in the magnetic flux. Kind of weird, right? Um, so this again is nature wanting to resist that particular change. It is wanting to resist the idea that the flux is increasing in this direction and therefore creates its own current to push back by generating a magnetic field that pushes in the other direction. Kind of weird, isn't it? So let's take a little bit more of a look here in depth. You can read through this, pretty much says the same thing that I had just told you. So you've got an increase here due to whatever reason, an increase in the magnetic field or the motion of this thing, what have you. The current following the right hand rule is going to be produced so that a magnetic field is induced to cancel this out. So if you uh, see that you have an increasing field in one direction and you want to cancel that out by increasing the magnetic field in the other direction, the current is created so that the magnetic field that is produced resists that change that is making. So if the current is flowing this way, following the right hand rule, if you curl your fingers in the direction in which that current is being produced, the magnetic field produced from that current will follow your thumb on the right hand. Same thing over here. If the current is flowing in this particular direction, uh, in order to produce a current, magnetic field to resist, say, a change in this direction, your right hand, when you curl your fingers this way, will produce a current or a magnetic field that is pointed in this direction. So this diagram here, figure 21.15, it's kind of busy, but it gives you a very good description as far as how Lenz's law works. So you've got a north pole that faces the loop. You've got a magnet that moves down. As the magnet moves down, you're seeing a change in the magnetic flux from time 1 to time 2. That change is basically here represented as the subtraction of the two vectors, this one from this one, and this is going to be the change. So as that north pole moves down, this is the change in the flux that we see. We want that change in the flux to be counteracted, or nature wants that change in the flux to be counteracted. It needs a magnetic field that goes this way in order to oppose that change. Now, if your magnetic field needs to point this way from the current in order to change it, which way is the current going? Well, if you'll take your thumb on your right hand and point it in that direction, basically pointing up, you'll notice your fingers curl in this direction. That is the direction of the current that is needed in order to oppose that change. If you take the south pole of that magnet and move it down towards this, you're going to see that there is a change in the magnetic flux in this direction. So you're seeing that the change goes from here up to here. So your change in the magnetic flux is going to be this. You need a current pointing in the opposite direction in order to be able to stop that, or at least try to resist it. If your induced magnetic field is pointing in this direction, if you take your right hand, point it down, and then see which way your fingers curl, your fingers will curl in this direction, and this is the direction of the current. If you have the north pole of the magnet oriented towards a loop like this, but it starts moving up, then you are seeing the change in the flux go from here to here. It's basically being reduced. This is the amount of reduction that you're seeing. That's the change in the flux. It's going from this to this, so it's being reduced, pointing in this direction. We don't like that. We are wanting a change in the magnetic field pointed in this direction to cancel that out. In order to be able to do that, we have to have a current flowing in this direction. We want the magnetic field pointed in this direction. We have to then take our thumb, point it down, see which way the fingers curl. In this case, it has to curl in this direction. Finally, over here, if we have a south pole and the magnet is still moving up, we're seeing the change in the flux going from here down to this direction because the number of field lines are getting smaller and smaller. Because of that, the change in the magnetic flux is actually pointed in this direction. Because of that, nature doesn't like that and wants to counteract that. It will do so by inducing a current in this particular wire in order to generate a magnetic field pointed this direction. So again, if you take your fingers pointed upwards, or take your thumb pointed upwards, because that's the field direction that needs to happen. In order to resist the change, your fingers curl around like this, and that is the current that is produced. So in all of these cases, the induced current tends to preserve the status quo by opposing the motion or the change of flux that originally induced it. So let's take a look here at some of the problems that we have here. So we've got this figure here that shows a region with a constant magnetic field. So the magnetic field is not changing. And it points into the page. The X here, think of the magnetic field representation here as an arrow. And if you see an X, it means that the arrow was fired into the page because you're looking at the little fins on the back of the arrow as it travels away from you. If it's a dot, that means it's coming towards you. The arrow is coming towards you. That's the way I was always taught to look at it. So a circular loop is initially dropped from above the field so that it falls into and through the magnetic field. As it falls, at what point does it carry an induced current that forms counterclockwise, flowing around like this? Well, a solution here is that in the middle of the magnetic field, the flux isn't changing, so there's no current in the loop. So therefore, it can't be in the middle of the magnetic field. As the loop initially falls into the magnetic field, it increases. In other words, there's no magnetic field, but now it crosses into this. So it is cutting the magnetic field. There's going to be an increased flux in the loop. The induced magnetic field opposes this increase, meaning that it must point in the opposite direction as the magnetic field. So in other words, as this falls this way, it increases the number of field lines that get cut right here at the top. Because it increases the number of field lines as it falls through, it has to produce a magnetic field that counteracts what it's experiencing, which is going through the page. Therefore, in order to be able to do that, it has to create a magnetic field that's coming out of the page. In order to be able to produce a magnetic field that comes out of the out of the page in order to resist the change, then you would take your thumb, your fist on your right hand, and point the thumb in the direction of the needed change in the magnetic field, which would be upward. When you do that, your fingers curl around in the counterclockwise direction. That's the direction that it's asking for. The current is counterclockwise. That induced current is counterclockwise. So therefore, your correct answer is A. As it leaves the field, down here at the bottom, which is your third choice, we're no longer cutting as many lines. Because we're no longer cutting as many lines, we want to be able, that flux is changing, it's reducing. Because it's reducing, nature doesn't like that, so it wants to be able to produce a field in order to be able to compensate for that. So in order to be able to compensate for that, it has to restore some of that magnetic field that it was experiencing. In order to be able to do that, we want a field that's going to go into the page. So if we take our right hand, point our thumb in the direction of the field as we need it to be, in order to keep the magnetic field the same, point it into the page and our fingers curl clockwise. Well, that's not the answer that they're looking for here. They're looking for something that's pointing counterclockwise. In this case, it would be this one, which refers to answer A. So let's take a look here at another example. We're going to apply it to a conductor moving in a magnetic field. So this figure shows the slide wire generator. The conducting rod is moving to the right. So we're going to find the direction of the current induced in the loop and the direction of the force exerted on the rod by the resulting induced magnetic field. So we've got a slide wire moving this way. If we look at this with the using the right hand rule, if we take V cross B, if we take our right hand, V is going to be pointed in the direction of the thumb. B is going to be pointed in the direction of the magnetic field, which is going to be into the page. Our palm of our hand is going to point in the direction in which the current or the current is going to flow in order to be able to produce the magnetic field, which is going to resist change. In this case, it points up in that particular direction. So the magnetic or the current that is induced in order to generate the magnetic field, in order to restore whatever magnetic field is being lost or to counteract whatever is being gained, has to be pointed up. And therefore the current is going to then rotate in this direction. So there are some tutorials there that would be good to go through. I won't run them here because of memory space, but let's do go through this particular example of an induced current in a resistance capacitance circuit. So we're going to apply Lenz's law to a loop with a changing magnetic flux. So we've got loop A, and that's part of a resistance capacitance circuit. When you close the switch, the capacitor discharges. While the capacitor is discharging, what are the directions of the induced EMF, the induced current, and the induced magnetic field in loop B? So when you close that switch, the current is from the positive to the negative plate of the capacitor. It creates an upward magnetic field through the loop. So as we've learned in section 19.8, the current decreases with time. In other words, the current as we see it here begins to dissipate because there's only so much charge that is accumulated between these two. So the flux through this loop B ends up decreasing. To counter the decrease in the flux, the induced magnetic field must point upward, meaning that the induced EMF and the current in loop B are counterclockwise as viewed from above. Um, again, this is all about trying to restore the magnetic field that was either lost or to resist any sort of change in the magnetic field as it increases. So that's what Lenz's law is about. Now, let's go on here to motional EMF. So when you've got a conductor moving in a magnetic field, we can gain insight into the resulting induced EMF by considering the magnetic forces on charges in the conductor. So in this figure, we've got the same moving rod that we had discussed before, separated for the moment from the rest of the U-shaped conductor. Magnetic field is again going to be uniform, pointed into the page, and we give the rod a constant velocity to the right. So a charged particle Q in the rod that experiences a magnetic force of QVB. So in the following discussion, we're going to assume that Q is positive, and in that particular case, the direction of this force is upward along the rod from B towards A. The EMF and the current are the same whether Q is positive or negative. So we've got the direction of the induced current. This again follows a right-hand rule. The velocity, if we use a right hand, pointed out to the right, B is pointed into the field, our palm is up. Therefore, the force is going to be this way. The resulting charge separation creates a canceling electric force in this direction. So the motional EMF in the moving rod creates an electric field in the stationary conductor. So again, the magnetic force causes the free charge in the rod to move, creating an excess of positive charge at the upper end and negative charge at the lower end. And this creates an electric field in the direction from A to B, which exerts a downward force on the charges. The accumulation of charge at the ends of the rod continues until E is large enough for the downward electric force to cancel exactly the upward magnetic force, and therefore these two become equal and the charges are in equilibrium with point A at higher potential than point B. So when the magnitude, the potential, what is the magnitude of the potential difference? That's going to be equal to the electric field magnitude multiplied by the length of the rod. From the preceding discussion, we know that the electric field is equal to the velocity times B. So The voltage here is going to be E multiplied by L, or VBL. So suppose the moving rod slides along a stationary U-shaped conductor, forming a complete circuit, just like what we had here. No magnetic force acts on the charge in the stationary conductor, but there is an electric field caused by the accumulation of charges at A and B. So under the action of this field, a current is established in the counterclockwise direction around the complete circuit, just as you see here. Up here, we had an accumulation of charge, positive charge here, and negative charge here. There's no pathway for it to start making motion. Now, if we put this little, the rest of the stationary conductor into its U shape, now we've given it a pathway to start conducting. So this moving rod has become a source of EMF, and with it the charges move from higher to lower potential, and in the remainder of the circuit, charge moves from higher to lower potential. So that's emotional EMF. As with the other EMF, we'll denote it with epsilon. And when the velocity, magnetic field, and length are mutually perpendicular, this is what we end up with. If the magnetic field direction is parallel to the rod, then there is no EMF. So let's take a look here. Forces on a square loop. So we've got a square loop here, and that is pulled upward from between the poles of the magnet. How do the magnetic forces on the top and the bottom wires compare? Well, as the loop moves up from between the poles of the magnet, the flux through it decreases, and that induces a current. Lenz's law tells us that the net downward force acts on the loop, opposing its upward motion. But it doesn't tell us about the relative magnitudes of the forces on the top and the bottom of the wires. So we've got to consider the magnetic forces acting on these two current carrying wires. So first we determine the direction of the current. We could use Lenz's law, but let's use the right-hand rule. The wires move upward and the magnetic field points to the right. In other words, the wire is moving this way. That's the velocity. And the magnetic field points to the right because we're going from the north to the south pole. So by the right-hand rule, the free electrons in both wires experience a magnetic force out of the plane of the page. In other words, V cross B, if I put my fingers in those directions, I've got V and I've got B headed this way, V up this way, B headed this way. If we do the right-hand rule, they experience a magnetic force out of the plane of the page. Because the bottom wire is in a stronger magnetic field, its electron forces are greater. So the overall conventional current is clockwise as viewed from the north pole of the magnet. So in other words, as you look this way, it's going to basically rotate, go here to here to here to here. The current in the top wire is therefore out of the page of the plane, and the force on the wire is upward. The current in the bottom of the wire is into the plane of the page, so the force on that wire is downward. Because the bottom wire is in a stronger magnetic field, the force exerted on it is stronger, so the correct answer is D. The forces are directed upwards along the wire and downwards on the bottom wire, and the force on the wire on the bottom wire is going to be stronger. So let's take a look at this particular practice problem. In this example, we'll apply the concepts of the motional EMF and Lenz's law to the slide wire generator. So supposing the length of the slide wire rod is 0.1 meters, its speed is 2.5 meters per second. The total resistance of the loop is 0.030 ohms. And the magnetic field is zero point 0.6 teslas. So let's find the EMF, the induced current, the force acting on the rod, and the mechanical power needed to keep the rod moving at a constant speed. So we use equation 21.6. We have all of our pieces of information there we can plug in. From Ohm's law, the current in the loop, V is equal to IR, just rearranged here. We'll come up with that. Lenz's law tells us that the induced force acts on the rod opposite in the rod's direction of motion. Magnitude of that particular force ends up being I times L times B. So to keep it moving at a constant speed, the force equal in magnitude and opposite direction of the induced force must act on the rod. So the power, which is going to be force multiplied by the velocity, is going to be this. Now let's move on to eddy currents, not cousin Eddie, but eddy currents. So we've looked at examples of induction. The induced currents have been confined to well-defined paths in the conductors and other components forming a circuit. But many pieces of electrical equipment contain masses of metal moving in magnetic fields or located in changing magnetic fields. In situations like these, we have induced currents that circulate through the volume of a conducting material because their flow patterns represent swirling eddies in a river. They're called eddy currents. So, for example, if you consider a metallic disc rotating in a magnetic field perpendicular to the plane of the disc, like here, um, it's confined to a limited portion of the disk's area. So, sector OB experiences a sideways magnetic field force towards the right that opposes the rotation of the disk. The return currents lie outside the field, so no such forces are exerted on them. The interaction between the eddy currents and the field causes a braking action on the disk and a conversion of electrical energy to heat because of the resistance of the material. So you can see the eddy currents coming up here through that cross-sectional area B. So the shiny metal disc in the electric meter outside a house rotates as a result of eddy currents that are induced in it by magnetic fields caused by sinusoidally varying currents in a coil. Similar effects can be used to stop the rotation of a circular saw quickly when the power is turned off. Eddy current braking is also used on some electrically powered rapid transit vehicles. Magnets mounted in the cars induced eddy currents in the rails. Resulting magnetic fields cause braking forces on the electromagnets and then also on the cars. So finally, the familiar metal detector seen at security airports or checkpoints in airports operate by detecting eddy currents induced in metallic objects. That's how they find it. So similar devices are used to locate buried treasure, which is kind of what you're seeing here. So you got the pulse of the current going on here, and then if that gets disrupted or by eddy currents, then you can see here that you found something. And you can kind of see the same thing here. You're going through a metal detector, you can kind of see with the eddy currents what sort of changes in the current you're able to find. So really kind of fascinating stuff.